You know, when being an Army guy, when we were looking for places to do maneuvers, we always tried to find a place that had hills and green and trees and stuff. So we always knew to ask an Air Force officer where the hell the golf course was, because they always knew. That was the one thing that you could count on them knowing. So for my talk, we're going to kind of move up a little bit and move up the food chain, if you will. And I'm not a physicist. I'm a computer systems person, both user, and then I used to run computing at Los Alamos, and then some of the other things we've done in other companies. And so we'll not talk much about physics except what our customers are doing, and we'll mostly be focused on how do you apply these things. And then secondly, would also say that our company and our customers are a little more like Nike, I think. And it's with, all of the theory behind quantum annealing wasn't done, still isn't completely thought out and all the rest. But this is more an approach of sort of just do it. And that's what D-Wave started with at the start, and that's what our customers are doing. And I think you'll hear from Martin Hoffman later on at Volkswagen about that, and you'll hear from Alejandro perhaps in various places to talk about machine learning that he's done on our machine and others. So that's sort of the approach here in the spirit. So we'll talk a little bit about our type of quantum computing, and I'll start with the picture of Richard Feynman, who in fact, starting in 81, talking about it, paper in 82, and I met him in 1983. It was the 40th anniversary of Los Alamos, the Manhattan Project, and he was the person who ran the computing, what was then called the computation division at Los Alamos starting in 1943. And I was about the fifth person to run the computing division at Los Alamos. So he gave this talk in April of 1983, again, 40th anniversary of Los Alamos. And you would see at 9 o'clock, his name, giving a talk, Tiny Computers Obeying Quantum Mechanical Laws. And you would see lots of other Nobel laureates who were at Los Alamos during the war and then had all come back for this. And this was the first time I'd ever heard of the idea of a quantum computer. And a couple of days later, Feynman and Robbie and Hans Bethe was still alive, and others, Edward Teller, wanted to see the modern computing facilities at Los Alamos. And at the time, we were the largest scientific computing facility in the world. We had 5 crays, and I'll always remember standing in front of one of those crays saying, and this thing can do 160 million calculations a second, and we have 5 of them. And so, so we can do like 800 million calculations a second. And I can't do Feynman's accent, but he said, young man, someday all these big crays are going to be replaced by quantum computers. And I said something notable like, wow, or cool, or I don't think we were up to awesome yet. But that was the first that I had ever heard of quantum computers. And here we are now, 35 years later, and Los Alamos became our third customer in the last year and a half or so, and Oak Ridge has just become a customer of ours as well. So that idea has taken a long, long time, and there are many different paths and forms to it. And when you're going to build a computer, you need to think about what architecture you're going to use and then how are you going to build it. And those two play together, and we'll skip over the devices and quantum communications and those sorts of things. But if you're building a quantum computer or thinking about building one, the major approaches to it today are the gate model that we've heard the most about this morning, and then annealing, and then topological. And Julie Love from Microsoft will probably talk a little bit about topological tomorrow. And those are the 3, and then you marry sort of the architecture that you're following with how are you going to build qubits. And these slides will all be available to everybody. This was from Science about going on 2 years ago now, and I thought it was a good sort of introduction to the different types of qubits that you could use. Most of us are using superconducting qubits. I and Q, who will be here today and tomorrow, are using trapped ions, and then Microsoft is using topological. So again, if you're interested and kind of new to this at least was an interesting article and sort of a summary of the different types of qubits that you could use. And again, you assemble those into an architecture. And so from now on, then I'll stick with kind of our architecture and our approach to it. So we use an approach called quantum annealing. And there's been a computational approach called simulated annealing that people have used now for the last 70 years. And how many of you have ever used a computational technique called simulated annealing? A few. And basically what that technique does, and it was first, this is sort of a predecessor of it, but a paper by Nick Metropolis and the Tellers and the Rosenbluths from 1953. And basically, and I love the title, Equation of State Calculations by Fast Computing Machines. These fast computing machines were machines that had names like Maniac, and machines that they had built themselves generally. And the idea behind the simulated annealing was that you would, if you were looking for a minimum or a maximum, you would compute for a while and then stop, and then kind of look around and pick a better or maybe sometimes a worse place to go, and then you would compute some more and stop, compute some more and stop, compute some more and stop. And that sounds a little bit like an annealing process if you're making a sword, where you have a piece of metal, you heat it, and then you beat it into shape, and then you dip it in water, say, and cool it. Then you heat it again and beat it some more into shape and cool it again. And that's called annealing. Thermal annealing or physical annealing. And so the idea was, here was a way to do a computational technique that they ended up over a period of years being called simulated annealing. So it's an idea that had been around for a long time. And then toward the end of the 1990s, Professor Nishimori at Tokyo Institute of Technology and his student Katawaki-san wrote a paper and said, maybe you could apply something like that technique and be able to come up with a quantum architecture and build a different type of quantum computer. And then Eddie Farhi and gang at MIT had some more ideas about being able to follow the adiabatic process to be able to build a computer. And at about the same time, there were a group of young PhD physics candidates, a couple of them at the University of British Columbia, and they had just taken a class in entrepreneurship. And they said, let's start a business. And great, what kind of a business? We'll start a physics business. Okay, what are we going to do? Physics. But that didn't lead to any big business, so what they started doing were collecting patents around things quantum, which was what they knew about. And you would see today that D-Wave has 150 plus patents, and that started nearly 20 years ago. And then after a while, they, like lots of the rest of us, I think thought in other businesses that, we have this great patent portfolio and it'll be worth zillions of dollars. Well, it only is if someone willing to buy it. And so no one was at that time. So then these ideas were coming along from academia about how you could build this different type of quantum computer. You had these entrepreneurs who had a great background or founding in quantum physics, and they wanted to do something, build a business, but how are you going to build it? So the architecture existed, the people existed, the desire to have a startup company and do something existed, but how are you going to build it? Well, with all due respect to our friends from Northrop Grumman who are here, there was a company, a defense contractor in the US called TRW, and they'd been building superconducting circuits for the government. Northrop Grumman, or what eventually became Northrop Grumman, bought them and decided they didn't want to build the superconducting circuits anymore, so they closed that down. So there were a group of people who sort of by coincidence met these entrepreneurs and said, we think we could build qubits, superconducting qubits. And we don't have a job, and so maybe we could help you because we know how to do the qubit part. You know the architecture, you have the business, and that's really what led to D-Wave almost 20 years ago now. And the first customer was Lockheed Martin, and their machine is housed at the University of Southern California down in Marina del Rey in Southern California. They started with a 128 qubit machine, and I agree with John about the importance of the quality of qubits. Our approach is a little different, and we'll talk about that as we go. But they started with 128 qubits and then upgraded it to 500 and then are now running a 1,000 qubit machine. Google and our friends here at NASA Ames and USRA became our second customer starting about 3.5 or 4 years ago with a 500 qubit machine upgraded to 1,000 qubits. And then just a few months ago, we've completed the installation of the first customer 2,000 qubit machine. And that's the one that's located about, I would say, 3/4 of a mile in that direction, and the one that they've been running on since. Los Alamos became our third customer. Temporal Defense Systems is a company that you'll probably never have heard of and never will much. Cybersecurity is their application for their end customer. And then Oak Ridge is starting to use our cloud services and has about 20% of one of our machines to get started. And then we have a host of other customers who access our machine via cloud. And again, Martin will talk about that from the Volkswagen perspective. So this machine is different than anything you've ever computed with, or certainly than I ever did. And this is kind of how it works. So if you could imagine that you had a problem that is like the Alps, so mountains and valleys, what this computer does is, without adding or subtracting, it finds the lowest valley or valleys in the Alps, probably. So it's not guaranteed that it does, and of course it's not really a three-dimensional mountain range with valleys in it. It's really an n-dimensional energy landscape, and we're finding a low energy solution to the problem. So the challenge is, how do you map a problem onto it? And that's really where a lot of work needs to be done. But people, again, are saying, let's just, and I'm going to spend most of the talk showing you kind of what people have been doing with it and how to map problems onto it. But that's the way to think about it, is n-dimensional energy landscape, and it finds the lowest valley or valleys in that landscape, probably. One thing to note, though, is that unlike the world that we come from, this machine is more dependent on finding an answer is more dependent on the nature of your problem. So if your problem ends up being really like the Alps with steep mountains and a very low valley someplace, and you run it 100 times, you may get 91 answers in that lowest valley, and 2 in the next lowest, and 1 more in the next lowest valley, and then there may be a scattering around. But if your problem, instead of being steep mountains and low valleys, is more like the Sahara Desert, so flat with some sand dunes, you'll get answers all over the place. If you run it 100 times, you'll get answers all over the place. So in our case, again, the conditioning of your problem is important to the quality of the answer, or the type of answer that you get back. There are applications for both types, optimization on the one hand, and then maybe training machine learning applications on the other. So it's quite different than anything we've used, and I just put this together to kind of show you. So, in the supercomputer world, I've put an Intel 64-bit architecture here in the middle of the chart, but performance there is measured, in bazillions of floating point operations per second, flops. We don't do any floating point operations. This machine doesn't add or doesn't subtract in a native mode. Precision of the machines you're used to is 64 bits. When you create this energy landscape, you really only today have about 5 bits of precision to be able to create that. So sort of you're limited in the fidelity, if you will, of the dimensionality of the problem that you can create. And in terms of doing millions and billions of instructions per second, our machines, depending on the model, do about 5 to 10,000 instructions per second. But each of those instructions is solving this energy landscape and finding a low valley in that energy landscape. This is, for those who are computer scientists, this is the really, really, really reduced instruction set computer. It has 1 instruction. So it's really easy to learn the instruction. The little challenge is, how do you map a real world problem onto it? And we'll show you some examples from that. And we're starting to sort of work our way up to create software tools to make it easier to look at. It runs at near absolute zero. The chip itself is superconducting. It's about the size of your thumbnail, uses virtually no power. The entire system uses about 25 kilowatts. That's for all of the cooling and interface to the networks and stuff. So it's relatively low power. 2,000 qubits today. We have about systems 5,000 qubits or so on the horizon in a couple of years from now. But the maturity one, I think, is important here, and it is using our machine is like it must have been in the the mid 1950s at IBM or something. And, when they were just switching from tried and true vacuum tubes to these new things called transistors, were they going to work or not? And Fortran, a now dead language, hadn't even been invented yet in 1955. And but in those days, if you did something on one of their computers, it was probably the first time that it had ever been done. And that's kind of the way it is here today. Also, whether you're using our machine or whether you'll be using the Google machine or the IBM machine or the Microsoft machine or Rigetti. So it's a place for pioneers. And you'll read in The Economist magazine and other places that quantum computing is mainstream. Well, it's a different mainstream than I'm used to. And, again, we've installed about $50 million worth of computers, and we have another roughly $30 million on order, but it's not mainstream yet. And so it's a place for pioneers, but it's going to have a huge impact. And part of the reason I like to do it is I think we can have a bigger impact on the future of computing with quantum computing than we did with Cray Research or than with Silicon Graphics or some of the other startups. So it's really cool, a lot of potential, but a lot of hard work to be able to realize it. This is what our computers look like. They look like a big box, 10 feet by 10 feet by about 10 feet high. Each of them is a Faraday cage, really. The quantum calculations or the quantum states are fragile. You have to protect them in lots of ways. These were designed so that ergonomically you could fit 3 people in the box at the same time to work on it. So if you opened up the door, there's a door on the back left of one of those boxes, and stepped inside, you would see a big can. It looks like a giant soup can about 2 feet in diameter by about 4 feet high. If you took that can off, you'd see another can and another can and another. And it's sort of like the Russian dolls. It's stacked one inside the other, and each of those is shielding. And if you took them all off, this is what one of the generations of our machines look like, and those cans attached to these gold discs, and within each of them we're stepping down the temperatures. So it's room temperature at the very top, liquid nitrogen temperature there in sort of the first layer, and then liquid helium temperatures down below. We're currently running the machines at between 10 and 15 millikelvin, which is a lot colder than it is in interstellar space. And I'm going to make sure we have some wood to knock on here somewhere, but when we just upgraded I think particle board counts as wood, when we just upgraded the Google machine, the Google NASA Ames and USRA machine, I think it had run 22 months without a failure, and the Los Alamos machine has been running for 1 year and 3 months now without a customer observed failure. So we're very pleased that we're able to do the engineering part to keep them running. The chip, that's what the chip looks like. And it's, again, it's about the size of your thumbnail. We won't jump into all of the details about it today, but we're glad to do that in other places. And in rough numbers, Moore's law is dead, but kind of long live Moore's law. In rough numbers, we've been able to double the number of qubits every couple of years or so and expect to be able to continue to do that. So our next stop is probably at 5,000 qubits. And for those of you who have used our machines, with a huge increase in the connectivity between the qubits. And so, in fact, our machines are not great today at traveling salesman problem, but I think when we get to the 5,000 qubit machine, we'll have much better connectivity between them, and I think we'll be better at traveling salesman problems. So this is sort of why should you care? And I've been doing computing one way or another for a long time, and in the end, people ask 3 questions. Can you help solve my problem? How fast? And what does it cost? And so we're just starting now to be able to help people at least look at parts of their problems. And in some cases, the performance has been getting up to sort of conventional levels of performance. In a couple of cases, maybe a little better. And we do know what it costs. I mean, these are supercomputer class machines. They sell for about $10 million. You can lease them for less. You can't get one on your desk yet. It's not a cell phone capable thing yet. So it's a supercomputer class machine. And so basically our machines are oriented toward solving particular types of optimization problems, probably machine learning. Monte Carlo and sampling is an underlying case for that, and we're just starting to investigate this broader area of material science, if you will. So just a few examples of real world things that people are doing on our machines. These, I've taken slides from people's various presentations at our users group meetings or at other places. These are available. There are some websites at the end here that I have probably 30 or 40 different presentations on them of people actually running. I call them proto-apps, prototype applications on our machines, and you're welcome to look them up and talk to the people who are doing them. So in sort of big picture stuff, what the five biggest customers are doing are Lockheed, again, was first along with USC, and Lockheed started with software verification and validation, and then there's a collection of optimization and performance characterization and physics. Of course, here at NASA Ames with Google and USRA, it's started with machine learning, and then the NASA and USRA folks looking at a collection of other really interesting problems. Los Alamos has probably the broadest set of proto-apps that you can see here, and we'll jump into those in a second. Temporal defense systems, cybersecurity, and we think Oak Ridge will be similar to Los Alamos, but probably more emphasis on material science and chemistry. And so the next 15 charts or so that we'll go through very quickly are directly from the customers. And this is a slide that was used by John Sorrow, who's Associate Director at Los Alamos, of some projects that they've run on the D-Wave machine. And this sort of is characteristic of what you would see. Over the last 2 years, they've run about 20 different projects where they funded people to go run on the D-Wave machines. And about half of those are optimization, about a quarter are machine learning, and the other quarter are a collection of other things, including, as you would see, one good idea. And this is the collection of what all of those projects are, and you would see they range from deep learning to over on the right side, graph partitioning for electronic structure problems, and there's a terrorist network, investigating terrorist networks, a graph problem, looking at terrorist networks on our machines is yet another. And again, these are Los Alamos slides that we borrowed from them, and again, I won't spend much time on them, but those publications are all listed at the website that's on the bottom of this chart, and then again we repeat it at the end. And some of the things they've done are, this was a machine learning one to see if you could use our machine to sort of go beyond recognizing fuzzy digits and numbers, fuzzy letters and numbers, to maybe starting to use it to see if you could recognize faces. They had some success at doing that. The next one is combinatorial optimization, and if you would look sort of in the middle part on the right, D-Wave beats simulated annealing by a factor of quite a few, and but the problem sizes are small still, not compared to the state-of-the-art that you could do. And this was another one, the graph partitioning, Sue Misnewski, graph partitioning for electronic structure problems. And in some cases, the results that they got on D-Wave machine were better than they could get with classical techniques. So this is, again, you know, we're starting to see some things which are sort of getting to the state-of-the-art and in a couple of cases better. You'll hear about traffic flow optimization from Martin this afternoon. And this was a great application, so we'll just, we had a great announcement of it last March, and it's the first quantum application that I know of that you could explain to your parents or someone in the supermarket of how do you make traffic flow better. This from Booz Allen Hamilton running on our machines of optimizing satellite coverage, and won't go into a lot of details of it. Again, these presentations are all available, but a heterogeneous approach as we talked, and beginning to see the results from using the D-Wave were pretty good. And this one from Japan, a company called Recruit Communications, who amongst other things has internet services business. And so they wanted to see if they could use our machine for an optimization application to see if they could do two sorts of optimizations. One is, so this particular problem is, how do you get ads on, when you're doing something on the internet, on your phone or your laptop? The idea is to maximize the click-through rates from their customer. And so they were trying to maximize click-through rates and also at the same time find the best way to have the ad spend be paced through the day. So sort of a dual optimization problem. And in fact, they found that using the D-Wave machine, quantum annealing found a better solution than the greedy method that they were using. And we're now moving on and working on other projects with them. The next one they're talking about, one of the next ones they're talking about might be a restaurant recommendation service. So, again, another sort of combined optimization with a little bit of machine learning thrown in. And then moving on to machine learning, this was a paper by Thomas Potok and group from Oak Ridge, and then some of our friends from USC and University of Tennessee, looking at which architecture is best for complex deep learning problems. And this was 6 or 8 months ago, I guess. And interestingly enough, the architectures, there probably is a role for each quantum computing, HPCs with GPUs, and neuromorphic. And interestingly, again, this is right out of their paper, is that the D-Wave class machines might be best at helping train models. We're not great at large sizes yet, but that architectural fit seems to be there. And this was from the users group meeting that we had at the end of September in Washington, D.C., and a fellow from an ISV really called QX branch. I think the X might be silent. But he said, let's see if we could apply machine learning to the last US presidential election. The polls were incredibly wrong, and including right up to the night of the election. And so he said, maybe we could use the D-Wave and go back and look at the same election poll data, the raw data, over the last year or so, and see what the D-Wave would predict. And lo and behold, so the number one thing was to see if you could do that, and then secondly, see what the results were. And lo and behold, he was able to do that, and the D-Wave proto-app, I would call it, actually started predicting early, that Trump actually was making headway, and it started predicting that Trump's campaign was rolling along. Didn't show that he was going to win, but it started showing that he actually had some chance, more than, I think, 1.8%. So quite interesting thing. And then applications in machine learning from our friends at Lockheed, Steve Adachi. Alejandro is really one of the deans of machine learning, and folks at Los Alamos looking at a collection of things. And then this is, again, I think pointing toward the future. This in materials, sort of material science, I'll call the broad area. And one of our fellows was able to take a small, simple three-dimensional lattice and map it onto our two-dimensional array of qubits, and then begin simulating the quantum behavior of that particular little device. And I think over the next few months, you'll see 2 or 3 others, things like this coming along from us. So all of the presentations that I have talked about are listed at these places. Again, you can have all of these slides and go to those various websites. And this is a different approach, but it's a little hard to conceptualize how do you map your problem onto it, but you can do it, and you can do it today. And so we'll hear more about that as we go through the next couple of days. With that, would be glad to try to answer any questions, and if there are simple ones, I'll ask Matt to answer them. Like, where's the golf course? I think we're ready for the break. Oh.
Excuse me, do you see quantum cryptography as a technology we could expect in the near future?
Not on our machines at any time soon. So we don't run Shor's algorithm. We don't promise to be able to run it. There are approaches, we believe, where we can factor. We have a brute force way of being able to factor numbers on our machines. We can talk about that later if you want. But not very large numbers. We've factored numbers up to like 32,000, which isn't of a scale that anybody really in that world is interested in. However, when we get to the point, or where the gate model folks get to the point where you have machines that for sort of general purpose things really are hundreds of millions or billions of times faster, even if you can't run Shor's algorithm routinely or reliably, there probably will be things, different different encryption techniques that you could invent that you could never match on traditional computers just because of that raw speed difference. So I wouldn't be surprised that over the next few years, in addition to Shor's algorithm, which I think is a long way away from production orientation, it's going to require the error correction that was talked about earlier. I think there will be other techniques, and we may play a role in those, but quite a ways away. So I'm not concerned about people being able to use our machines or the others in the near term to break existing codes. But over the long term, I think there will be new ways to be able to create codes, encrypt codes. So with that, I think we're all ready for a break, and I can't see anyone out there. So we'll be around the next couple of days. There are 5 or 6 people from D-Wave here, so please feel free to ask us anything you'd like. And again, we'll make all these available to you. Thanks very much.